Coming next, a technical introduction to the Archimedes computer.
These computer pictures are being generated by the Archimedes, a desktop 32-bit micro which is based on a reduced instruction set chip. The amazing thing about this machine is the speed of execution. Well, here's another demonstration. In fact, this program took just a few minutes to write, and believe it or not, it's only this dozen lines of BASIC. This is the Archimedes 305 machine, one of two new BBC micros. As you've seen, it has very impressive graphics which provide the user with a friendly interface known as WIMPs. That stands for Windows, like this one here, icons, these symbols that you see at the bottom, there's the palette, notepad, diary, clock and so on. Then menus, I can call up a menu just here, and pointers. Well, in this case, it's an arrow I've been pointing with, and that's operated by this gadget, which is called a mouse. But WIMPs are pretty standard these days, so what makes this machine different? Well, in this technical introduction to the Archimedes, I'm going to be looking at the design of the machine and talking to Roger Wilson, who is one of the Acorn team that created it. We'll also be looking at part of the manufacturing process, and you'll see some simple troubleshooting. So what makes up the Archimedes 305? Well, it's the usual three-box design. There's the monitor, keyboard, and computer with a built-in 3.5-inch disk drive. By the way, the mouse is provided as standard. The keyboard has a similar layout to the latest IBM PC, except it has the added advantage of a copy button, which will keep the programmers happy. And of course, there's the familiar red function keys of the other BBC micros. At the heart of any micro is the printed circuit board. At first sight, the board for the Archimedes looks much like any other, except perhaps for these square chips, which are the main chipset. There's the CPU, memory controller, the input-output controller, and video controller. The memory over here, though, looks a bit more conventional. Well, I've displayed the main features of the board inside the 305 on this graphic. Here's the circuit board viewed from the side. Here are the 4 chips in the main chipset and 4 ROM chips for the operating system. There's 0.5 megabyte of memory, although this can be upgraded to a full megabyte by using vacant RAM sockets. The disk drive is positioned above this memory. So that's what you get in a basic 305. It is possible to upgrade further, though, by fitting an optional backplane, which takes 2 peripheral modules or podules, such as an input-output module or a ROM module. Here's 1 and 2 modules. Now, because they fit internally, modules are a very tidy way of connecting up all those peripherals without a lot of trailing wires. So that's the 305, but there are other machines in the range. The Archimedes 310 is also a BBC micro. As you can see from the display, it's almost identical to the basic 305, except it has 1 megabyte of RAM already fitted. Again, there's the option of 2 modules on a backplane. The 2 machines in the 300 series are probably going to be used in education alongside existing BBC micros, where new applications can benefit from the high speed and the high resolution graphics. There are also 2 machines in the Archimedes 400 series. Here's the first. The board is slightly different from before. This time, there's room for 4 modules and the backplane is already built in. And you'll notice it's full width. There are 2 and 4 modules. The Archimedes 410 here has got 1 megabyte of memory, but there's also the hardware to support an optional Winchester disk drive. And unlike the 300 series, one can fit a floating point arithmetic module. The most obvious external difference is the absence of red keys. The top of the range system is the Archimedes 440. It differs from the 410 in that it's already got 4 megabytes of memory fitted and a Winchester disk drive with 20 megabytes of storage. Once again, it'll take 4 podules. Whilst the 410 can be upgraded to the 440, there's no upgrade path from a 300 series machine to a 400 series. The 400 series has a totally different circuit board. For one thing, it can support a very high definition monochrome monitor, giving a resolution of 1280 by 976. So the 400 in particular is seen as being used in computer-aided design work, where high resolution is essential. So that's the range of machines which extends from the 305 up to the complexities of the 440. Now you know what to look for, let's get inside a real machine. I've already undone the 5 screws on the back and sides, and the lid simply slides off. It's a robust metal case, by the way. Well, here's that circuit board that we saw diagrammatically a few moments ago, and viewed from the same angle. You might even be able to work out which machine it is. Well, here's your clue. There's no backplane, but this is the socket for the half-width version. So it must be a 300 series. In fact, it's a 310. Here's the power supply, and these small batteries down here keep the real-time clock running when it's powered off. This area is where you could fit a Win disk drive if you decide to upgrade. At the back, there are ports for, well, there's head, monochrome, and analog RGB. Then there's RS402, a power port, and Ethernet. These 2 removable plates will accommodate any podules. In fact, if you're fitting podules, you'll also be provided with a fan, which fits into the space on this side. Now, a lot of the board is hidden from view, so I've got a model showing the most significant parts. I've coloured the 4 main areas of the board, each associated with one of those big square chips. The bulk of the board deals with input and output. Of course, that looks after the keyboard, the mouse, disk drive, as well as the serial, printer, and Ethernet ports. Now, that's all managed by this input-output controller. These sockets, on the other hand, are managed by the video controller chip, which not only handles the visual display, but also produces some pretty remarkable sound, and in stereo. Now, here's the bit you couldn't see before. It's the memory. On a 310, all these positions will be fitted with RAM. On the 305, the second row sockets here will be vacant, ready for a dealer upgrade. There's one important area of memory that isn't controlled by this memory controller chip, and that's the operating system. The 4 ROMs which fit in here. They're controlled by the central processor, the Acorn RISC machine. And inside this innocent-looking piece of black plastic is the first of a new breed of silicon computer. That's RISC, or Reduced Instruction Set Computer. I've been joined by Roger Wilson, who helped design the chip in the first place. Roger, I know that RISC stands for Reduced Instruction Set Computer, but reduced compared to what?
It's been reduced compared with a conventional instruction set computer like the Motorola 68000, which you'll find in many machines nowadays.
You've taken away some of those instructions, I take it. So why? I mean, doesn't that lead to a less capable machine?
Well, when we look at the instructions that the machine needs to use when executing a program, we find that 80% of the time, nearly all of the time, just 20% of the instructions are being used. We take away the other ones, and the ones that are being used frequently, we optimise, we make the machine run as well as possible so that it all goes very quickly.
Can you give me an example of the kind of instruction that you could take away safely?
Well, one that we did take away on the Acorn RISC machine was the divide instruction. If we do need to do a divide, you open the manual at the right place and there's the equivalent sequence of 10 simple instructions to do the job.
Well, I write simple programs. What happens to my code once I've typed it into the machine?
Well, we've got a little picture that shows what happens. You write source code in a high-level language like BASIC, C or Pascal. That's fed into either a compiler or an interpreter, depending on what flavour the language is. That takes your English-like instructions and changes them into the actual machine code instructions that this complex instruction set computer needs to execute. This uses microcode to take the instructions coming at it, understand them whether they're simple or complex, feed them into the logic that actually does the job and produce a result at the bottom.
I see. So with a CISC, that's a complex instruction set computer, you've got one area of the chip that's standing by, taking in instructions and sorting out the complex ones from the simple ones?
Yes, it needs to look at every instruction as it comes in, work out whether it's complex or simple. This means that the simple ones always take 2 or 3 cycles as it's working out the difference.
So it's always going to be time-consuming?
It always takes a long time, yes.
So how are things different with the RISC chip?
Well, we still write in the source code, and guess what? It still feeds into a compiler or interpreter as appropriate. But we make a promise to ourselves when we design that compiler that it will only emit the simple instructions. So when we go down to the hardware, it's much smaller and it can be run much quicker because it only ever gets the simple instructions. So it knows in advance that there will never be any complex instructions. If the compiler needs to do a complex job, then it emits the equivalent set of simple instructions.
So you get a speed increase anyway, even if you're doing 7 or 8 different subtasks to simulate your complex instruction?
Yes, because the simple instructions of the RISC chip run so quickly, even though it needs to use more of them in order to do a complex job, the result is still quicker. You win both ways.
Well, it's an ingenious idea, but in one sense it's very simple. Why hasn't it been done before?
It took a long time in computer science to gather the evidence that meant that we could do this. So it's taken 20 or 30 years while we've analysed programs in a theoretic sense. The other thing is it may be simple, but it's a lot harder to actually do the design. With the CISC computer, we've got the microcode, which is essentially software to do the job. With the RISC computer, everything's locked into the piece of silicon. So if something's wrong, then we have to pay a lot more.
Did Acorn think up RISC? Was it their idea?
No, it began in America. IBM, of course, invented it. They seem to invent most things in computing. Then it spread to universities in America, where they were doing research into computer architectures. And finally, on the west coast of America, somebody put what was theory into practice. And at the University of California in Berkeley, they built the world's first single-chip RISC microprocessor in 1982. We began our research and design in 1983, after they proved that it could be done.
So it's taken you, what, 4 years to get it right?
Well, it actually took us about 2 years from starting the design in 1983 to having working ARM chips for our laboratories. We then proceeded to make all the support chips and write the software and design the actual computers that we see now.
So no way is this an experimental machine?
We have used them for a long time. The central processor itself we got back in April 1985, and we've made another one since then, which is what's in these machines.
You've made some very fundamental changes here. You've changed the brain of the machine, and it sounds as though you're doing away with compatibility with any other existing machines. Is that true?
It's not true at all. The source code that we're feeding into these compilers is identical, and this machine comes with a basic interpreter that can understand all the programs you wrote for previous Acorn machines like the BBC machine or the Electron. We can use the power of the RISC computer, which is going so much faster, to actually emulate the instruction order codes of previous computers. So instead of having a compiler that feeds it its own instructions, we can have a little interpreter that looks at instructions for, say, the 6502 microprocessor, translates that on the fly. And because we've got so much power, that actually works, and you can do it in real time. People can run programs from the BBC machine on this with no change, even to those bits that are written in the BBC machine's own machine code.
If you can get it to pretend to be a 6502, then presumably you can get it to emulate other machines. Are you doing that?
Yes, we are going to provide an IBM PC emulator. That is a program that pretends to be an Intel 8088 and the various support chips that are in an IBM PC.
Tell me, are other manufacturers tumbling over themselves to get RISC machines out?
Well, we've already mentioned IBM. They've been selling a RISC machine for a small while in the workstation market, and many people like Pyramid, Sun, Hewlett-Packard, Apollo are releasing RISC machines as the only way forward for increased power in the computers that they sell.
Do you believe it's the only way forward?
Well, all these people are doing it. It seems to be the only way to go.
Roger, thank you very much. Well, as I said, this is a full 32-bit machine, and that means there's a good deal of information to be moved about. For a start, there's going to be 32 separate signals coming in and out of our ARM chip. So we need to have 32 tracks for the data bus. There's also a 26-bit address bus, which means that the chip can address 64 megabytes of memory. Now, all those connections take up a fair amount of space and they make for a pretty complicated circuit board. In fact, a conventional double-sided PCB would have been horrendously difficult to design and would have been unacceptably large. That's why Acorn went for a 4-layer board. Now, here's a model of the construction. There are tracks on the top and the bottom, as you might expect, but there are also 2 other layers sandwiched in between, like that. These carry the power supplies. The connections between the layers are made by through-hole plating. Here they are. Now, you've got to be especially careful when desoldering a component from a 4-layer board like this, because the through-hole plating is the only means of connecting with the inner layers. So you should never attempt to remove a soldered-in component unless you have the correct extraction tool. The tool needed is a specialized desolderer, and they're few and far between. So we went to look at an example of one in use at an electronics assembly plant. It's difficult to see the action of the desolderer. It's effectively a soldering iron attached to a vacuum pump, which sucks up solder into a glass tube inside the gun. We set up a demonstration with a specially created pool of solder. Let's see the desolderer being used for real. Here's an Archimedes board which has been found to have a faulty component. The desolderer heats the solder from the underside, allowing the molten solder to be vacuumed up. Once the legs are freed, then the faulty component, an integrated circuit in this case, can be lifted out easily. But a reworking station is only one tiny part of the activities in this plant. In fact, this is the Rank Xerox Electronic Manufacturing Center in Welwyn Garden City, where the whole process of assembling components onto the Archimedes circuit boards is being carried out. That process involves several stages of automated component insertion. At each stage, boards are tested both electronically and visually. For some of the larger or odd-shaped components, hand assembly is required. Here it's up to an operator to place the components into position. The component legs are clenched by the operation of a foot switch. Following this stage, a board is taken by conveyor belt to be flow soldered. The soldering forms an electrical contact between through-plate connectors and the legs of components. First, the board is washed in an acid flux. The flow soldering itself happens as the board is carried over a bath of molten solder at a precise speed. If you look closely, you might just see solder welling up in some empty holes. Solder resist is applied to the bare boards before assembly to ensure that only the joints are soldered. Following the soldering, boards head off for a water wash to rinse away the hot acid flux left behind. The boards are next put through a thorough test by some very sophisticated automatic test equipment, in which the test bed, commonly called a bed of nails, sucks the board down onto test contacts. The equipment then provides a visual display as it checks on individual components and circuits in a functional sweep of the whole board. It then gives its verdict. Of course, few, if any, workshops will have the sort of test and repair equipment that you find in an assembly plant, so any serious faults will require that the board is sent off for repair. But how would you recognise a serious fault? An apparently serious problem might in fact be totally trivial. So let me show you a couple which could catch you out. For example, have a look at this. Well, the first thing you might do is start fiddling with the monitor. It obviously looks like a monitor fault, but it's not. In fact, the solution is as easy as this. I press the R button, and I switch off and on again. Quick pause, and there's a perfect picture. All I was doing was reconfiguring the system. This machine is capable of being configured in a way that suits the user. You can choose various options like which display mode you want, which monitor type, keyboard repeat rate, capitals or lowercase, the filing system in use, that kind of thing. All that's happened to produce that fault is I'd selected the wrong monitor type. There are basically two types of monitor, known as positive and negative pulse, and the system was simply expecting the other one. There are some standard settings for the configuration stored in ROM. If you have any problems, you can cycle through them simply by holding down R for reset while you power up. Now, you may need to do it several times, but once you're happy, the system will remember it even when switched off. Right, let me create another problem. There. Well, obviously I've done something physically to the machine, but I've managed to produce a fault which at first sight seems to suggest a monitor fault or a fault in the output somewhere. Some of the colours have gone. What I did, though, can happen quite easily. What was that? Well, the lead from the video was unscrewed and came loose. It's a very simply corrected problem once again. There we are. And not restricted to just Archimedes, of course. Now, one error message from the Archimedes might lead you to suspect the drives. It's this one. That of disk error. In fact, it's a good bet that the only reason for it is you've used an unformatted disk. Now, I can check that the drive is working by using this. It's the test disk, which is provided to all Acorn-approved workshops. There are dozens of tests on this disk. For example, this display is for checking the way a monitor scans. And indeed, it's also for checking the operation of the mouse. I'll move the mouse around up here, and yes, the pointer moves with it, so that's all right. But a test disk is not a lot of use if the problem is a dodgy disk drive or power supply. In cases like those, you'd need to look inside the machine. Well, there are a couple of straightforward checks you can make. If either of these leads has been knocked loose, then the display would announce that the drives were empty. In fact, yes, that one's loose now. So it pays to check them if you get that message. And you can test whether power is reaching the board by applying a voltmeter here at these spade connectors. Now, black is 0 volts, so measure everything to that. Yellow is plus 12, red here is plus 5, and purple at the back here, minus 5. So if any point is dead, then either there's a short circuit on the board, or there's a problem with the power supply itself. And of course, I could check for that by disconnecting here. As a rule, the most common reason for a user to need to go inside the machine would be to change these batteries, which are used for maintaining the machine's configuration. They ought to be replaced annually. Some educational users may want to add an Econet upgrade. Now, that's a simple job. It uses the same board as the Master 128, and it plugs in down here. That is such a simple job that there, I've done it. Now, of course, this Econet upgrade will allow you to transfer files from 5¼ disks, from tape and so on. Eventually, it's also possible that a user will want to upgrade these. They're the 4 ROM chips. Now, with care, that's reasonably easy. Although, unlike similar operations in earlier BBC micros, you have to fit a whole set of 4 chips each time. But these square chips should never be removed without the correct equipment. I've got the device that's used, though. It's this extraction tool. Now, it grips the chip at the corner, like that, diagonally opposite corners, and it lifts it vertically. If you try to extract a chip with anything else, you're likely to damage the board and the legs. Well, we've seen something of the design, the philosophy, and the construction of the Archimedes. So what can you do with it? Well, that's going to depend on the software that's written for it. Just cast your mind back to the first demonstration programs you saw running on the BBC. They look pretty stunning at the time, but think what you can now squeeze out of the same machine. Here we are at a new beginning, so just consider what the possibilities might be in 5 years' time, while we leave you with a few of the first Archimedes demonstration programs.